Energy-efficient samarium oxide thin films for semiconductor devices towards net-zero carbon emissions. This project is led by Associate Professor Insigne Dr. Wong Yu Hong. In microelectronics, the structure of MOSFETs includes the important dielectric layer, also known as the gate oxide, which serves as the insulator in a metal-insulator semiconductor structure. In order to continue downscaling of transistors, in accordance with Moore's law, the thickness of the traditional silicon dioxide dielectric has been scaled down over the years to improve performance. However, downscaling further beyond 1.2 nanometer is limited by fundamental physical limitations, leading to high leakage current. High K dielectrics can solve this problem as it allows lower driving voltage and lower leakage current, reducing power consumption and improving performance of transistor devices. Our innovation focuses on the development of energy-efficient samarium oxide thin films for semiconductor devices towards net-zero carbon emissions to replace traditional silicon dioxide gate dielectrics. As a proof of concept, we fabricated metal insulator semiconductor capacitors with chemically stable trigonal samarium oxide dielectric on germanium semiconductor substrate. The fabrication process consisted of several steps. First, we take a germanium wafer. The germanium wafer is diced into small pieces. Then, it is cleaned by standard RCA cleaning procedures to remove any contaminants that may degrade electrical performance. Once the clean wafers are ready, a layer of samarium metal is deposited onto the surface of the wafer pieces by physical vapor deposition under vacuum conditions. The samarium metal is then simultaneously oxidized and nitrided in a tube furnace at high temperature using nitrous oxide gas. Samarium oxide is thus formed. Aluminum metal electrodes are deposited on top to complete the MIS structure. Thus, the complete MIS device is obtained. The fabricated devices are then characterized by X-ray diffraction, which showed formation of trigonal samarium oxide. The devices were imaged using transmission electron microscopy, which showed a thin samarium oxide dielectric with an interfacial layer containing germanium. Small thicknesses of 4.3 to 6.9 nanometers was obtained. From X-ray photoelectron spectroscopy, we observed that germanate structures were formed which suppressed formation of gaseous germanium oxide. The electrical properties, specifically leakage current and capacitance, are measured for the capacitor devices. Electrical characterization showed a very high breakdown field of 13.3 megavolt per centimeter with an extremely low leakage current of 1 microampere per centimeter squared. Extremely high dielectric constant of 31 was achieved, compared to a value of just 3.9 for traditional silicon dioxide dielectrics. Highlights of our research include, first, advanced manufacturing process involving simultaneous oxidation and nitridation of samarium metal using nitrous oxide, reducing manufacturing costs and power usage. Secondly, suppression of volatile gaseous germanium oxide, which is a common problem in germanium-based devices. Thirdly, exceptional electrical performance that can improve performance and simultaneously reduce energy consumption. This innovation positions samarium oxide as a promising dielectric material for future high dielectric constant germanium stack-based metal oxide semiconductor technology, offering a path towards energy-efficient semiconductor devices with potential implications for reducing carbon emissions.